Okay, here we go. Good morning, everybody. Um, Today we are going to continue with topic 5.2. We're going to get into vertical circle problems and horizontal circle problems today. Okay, so here is a animation of a roller coaster, and it's just kind of showing all the forces that are present as it kind of goes through the roller coaster. So just a fun little animation there. All right, so when we are applying circular motion, some of these questions, they're a wide variety. So we need to kind of take our knowledge that we've acquired in the last couple lessons and apply those to solve these problems correctly. Probably the most difficult part about this is figuring out how to set them up. So two things we need to ask ourselves. Number one, is the circle moving in a horizontal or a vertical circle? And then the next question we need to ask, what are the combinations of forces that are causing the centripetal force? Remember, centripetal force is a generic term that can be used for any force that causes an object to move in a circular motion. All right. So those are two questions that we need to ask ourselves before we go and start solving the problems. So for horizontal circle problems, we'll start with those. A horizontal circle is any circle that lies flat and parallel to the ground. So a car going around a traffic circle is a great example of a horizontal circle problem. Okay. The path of a horizontal circle, it can be a complete circle or even just a portion of a circle. So either it can be a race car driver going in, constant laps around a circle, or it can just be a car making a 90-degree turn. Okay, it doesn't have to be a complete circle. That being said, if we are doing a question that involves a car turning just a 90-degree angle, we will still measure the basics, like what the radius would have been if it was a complete circle. Okay. If the object is on the ground, it is very common to say that the needed centripetal force is caused by the force of friction with the ground to cause that centripetal motion. So as the driver turns the wheel, the force of friction between the tires and the car is going to cause the vehicle to turn around the corner. Okay, so on horizontal circle problems, when something is turning a corner, the force of friction is equal to the centripetal force. Okay, that's going to make it kind of easy for us solving these problems. Okay, so if there's any takeaway from this slide, the force of friction is equal to the centripetal force of a vehicle turning. Okay, and same as last day, we're going to hang off on the examples to the end. I will post a calculation video for that. So we'll just hang off on solving these until the next video. Okay, and just a note that we'll talk about here. Since the car is moving around in a circle, there is a centripetal force caused by the friction between the tires and the ground. So as the tires push outward on the ground will push inwards on the tires. And you can actually see the force of the tires pushing the ground outwards. Like if you're driving down a gravel road and you turn right, you're going to be shooting the rocks outwards from the circle. Okay, so that's just kind of an info bit when we're solving this question. So this is how we're going to kind of combine and substitute our formulas as well. So remember from a couple slides ago, when we have a car turning a corner, the centripetal force is caused by the force of friction between the tires and the road. So we know from previous unit that the force of friction is equal to the coefficient of friction multiplied by the normal force. And we know from last day that the centripetal force is equal to the mass times the velocity squared over the radius of an object in circular motion. Okay, so we're just going to continue with the substitution. So because we're on a flat level surface, the normal force is equal to the force of gravity. The force of gravity is equal to mass times the acceleration due to gravity. So we'll substitute that in there. Because we have mass on both sides, those will cancel out. And then we will be left with the trying to find the radius of this curve. So that is equal to velocity squared over the coefficient of friction multiplied by the acceleration due to gravity. Okay, and we will use this to solve this question in the next video. Okay, example 2, same kind of thing. We're just going, centripetal force is caused by the force of friction, and we're all going to substitute that there as well. Okay, vertical circle problems. So these are going to be like roller coaster problems or something that's being rotated in a vertical circle on a string. Now, when we're solving these problems, we need to, again, what are the forces present that are going to contribute to the centripetal force? Okay, and we also need to know where the location of the object that is rotating is. So we're going to look at this particular roller coaster here, and we will say, as this cart moves through, it's going to be experiencing some forces, of course, as it goes through. At the bottom of the track, we're going to have the force of gravity acting down and the normal force acting up. So in this case, the normal force would be responsible for the centripetal force, okay? So just kind of a refresher, for an object to move in a circle, remember there must be a centripetal force acting on it. For objects at the top of the circle, the centripetal force is always pointing towards the circle, okay? And in this case, it's going to be down and negative. If the object is at the bottom, the centripetal force is going to be up and positive. And we're going to keep track of these questions using radius as a vector. So at the top, we're going to have a negative radius because it's pointing down towards the center. When the cart is at the bottom of the circle, the radius is going to be positive because it's pointing up towards the center as well. Okay. So number 2, consideration that we have to keep in mind as we solve vertical circle problems. The force of gravity is something that we often have to consider. And remember that the force of gravity will always point straight down no matter where it is. So if it's at the top, it's still going to be acting down here. If it's at the bottom, it's still acting down, right? Force of gravity always acts down. That's what keeps us stationary, right? Keeps our feet on the ground. Third consideration, in a situation such as a roller coaster, you need to show that there's a normal force exerted by the roller coaster tracks on the object it is touching. Okay, so at the top, it might be a little hard to conceptualize that the normal force is going to be pointing down. But think about it at the bottom, right? So when we're at the bottom, we have the normal force that is pointing up because it is the force of the roller coaster tracks that is being exerted on the cart, right? So if we're at the top, we're not going to have a normal force pointing up. It's going to be pointing down because that is the direction of the normal force of the track that it is exerting on the cart. Okay, and then lastly, if it's something spinning on a string, we need to consider the force due to tension exerted by this string on the force, because the force of tension is going to be responsible for the centripetal force of that object. So just a note, we kind of touched on this in the last slide. The normal force of the tracks is pushing against the cart, will be pushing the carts. So at the top of the cart, the normal force is going to be pushing down, again, because it's exerting that normal force from the tracks onto the cart. Okay, it's going to be pointing down at the top of the circle. Okay, and here's just a graph that summarizes this image on the right here. So the centripetal force is always going to be pointing towards the center of the circle. So if it's at the top, it's going to be pointing down. If it's at the bottom of the circle, will be pointing up. Gravity always points down. The normal force at the bottom of the circle is pointing up, as we just discussed, and at the top it is pointing down. And similar to the normal force when something is being rotated on a string, when it's at the top of the circle, the force of tension is acting down, and when it's at the bottom of the circle, the force of tension is acting up. Okay. So here is an interactive roller coaster, and I would like you guys to explore both of these links at some point. Okay, the first one is a little bit data oriented. So you're allowed to select the drop height and the height of some of the loops in the roller coaster, and it will kind of produce a spreadsheet on what type of forces that rider experiences and so on. So check that one out. And the roller coaster 2, that is the interactive that you see on the slide right now to the right. You are able to kind of manipulate the loops and the bends of the roller coaster track. So that's pretty fun. Make sure you turn on the force vectors, okay? This is a good kind of intro, and it will show us what the normal force is as the cart is moving along the track that you have created. Okay, so explore those two interactive learning tools. Those are pretty fun. Okay, again, we will solve these examples in the next video. And just something to keep in mind, so when the cars are at the top of the loop, it's going to be experiencing a force pulling it to the inwards, resulted by the force of gravity and the normal force. Okay, that's just what our free body diagram of the cart is going to look like at the top. And the centripetal force, in this particular case, when it's at the top, the centripetal force is caused by the force of gravity and the normal force exerted by the tracks on the cart. Okay, so when we get into example 5, this is the minimum speed the cars can move on the roller coaster to make it through the loop at the top. So a note for these types of problems is going at the minimum speed means that the cars will just barely make it through the top. The force due to gravity will supply all of the centripetal force needed to keep the roller coaster cart moving through the circle. There doesn't have to be any normal force supplied by the track at all. So with the normal force equal to 0, we can just cancel it. So we're left with centripetal force is equal to the force of gravity. Okay, that's going to make our lives a lot easier. Okay, so that is it for the theory portion of this lesson. So if you have any questions about this, again, please send me an email, send me a text. I'd be more than happy to help you. Yeah, so that's all I have to say about this kind of stuff. So feel free to tune into the next video, which will include all of the calculations that we have seen in this PowerPoint presentation. All right. So thank you guys, and we will see you soon.